Hello everyone, my name is Bruno Travensolo. I'm from Federal University of Uberlândia, UFU, in Brazil. In this presentation, I will talk about combining clutter reduction methods for temporal network visualization. This work was conducted by Jean Ponciano from UFU, Cláudio Linhares from USP in Brazil, Luiz Rocha from Ghent University in Belgium, Elaine Faria from UFU, and myself. First, let's talk about represent interactions. How can we represent interactions from telecommunication, social activities, or even biological and medical activities? In both cases, we have several elements interacting between themselves, forming a complex systems. So to represent this interaction, a useful tool is to use networks, complex networks, network science, that can gather informations between several elements, and we can use several tools to analyze these interactions. Temporal networks. Sometimes we are interested in the distributions of interaction over time. When we talk about complex network, in many examples, the studies focus only on the interactions between the nodes. But when you talk about temporal networks, we are interested in the interaction between the nodes and A and B here, for example, and also when the interaction occurred. So here A communicates with B in timestamp 1, B communicates with C in timestamp 2. It's interesting in these temporal networks to represent, to know the birth and death of nodes in the network, and to know bursts of interactions over time, and many other time-related properties that can be represented by using temporal network. We can analyze structural and temporal patterns, and also simulate and analyze dynamic process, for example, spread of infections. MSV for temporal network visualization. What is MSV? MSV means Massive Sequence View. It's an important strategy to visualize temporal networks. In this strategy, the nodes are positioned by lines in a specific order. For example, node A, node B, node C, node D. And the timestamps are represented in columns, 0, 1, 2. So we can represent one connection between, for example, node A and node B in timestamp 0 by, in the column 0, timestamp 0, by adding small circles in A and B and an edge between these two circles. So with this we can represent and see the evolution of the connection throughout time. For another example here, in timestamp 3, we have two connections, B and C, here, B and C, and C and D, here. MSV can be used to study or to visualize the spread of infection. For example, here we have the transmission path layout, where you can see the spread of a disease. For example, node B is infected in timestamp 1. Then it infects node C in timestamp 2, which infects node D in timestamp 3, and so on. So we can trace here the transmission path of the disease using this visualization. So what is the problem of the MSV layout? In real-world networks, we can have thousands, even millions of nodes and edges. So when we plot this using MSV, we can have a problem that we call visual clutter, where it's very hard to find patterns in this visualization, because all the nodes and edges are overlaps. So we have to adopt different strategy to improve the layout readability and enhance the analysis. To deal with the visual clutter, we can use different strategies. The first one is node order, which means that we can change the order of the nodes in the MSV layout. So it enhances the analysis by reducing the edge lengths. So when we reduce the edge lengths, by consequence, we also reduce the visual clutter. We use in this work the algorithm community-based node ordering, CNO. CNO detects network communities and finds suitable positions for the nodes in the MSV. So we use this algorithm to reduce the clutter as our first strategy. Our second strategy is edge sampling, which means that we can remove some edges from the network visualization and reduce the visual clutter with this remove. The algorithm that we are using here is Streaming Edge Sampling for Network Visualization, SEVs. SEVs enhance the analysis by discarding edges incidental to less relevant nodes. So this algorithm computes which nodes are more relevant and then remove the edges from non-relevant nodes. And also it can remove some nodes when the edge disappears between, for example, here these two nodes. If we remove this edge, also the nodes are removed from the visualization. The third strategy is Timeslicing, which means that we can change the temporal resolution of the network. The algorithm that we are using here is Adaptive Resolution, AR. AR considers local edge density to define the most suitable temporal resolution scale for each window of timestamp. It is a slide window to define the temporal resolution of the slide window. It enhances the analysis by reducing the amount of visual information through the merge of consecutive timestamps. So the main idea is to merge consecutive timestamps so we can reduce the clutter of the visualization. For this work, we analyzed two research questions. As the existing clutter reduction methods leverage a particular network dimension, node, edge, or time, we want to know. Question 1. Is the visual analysis enhanced when using the combination of two methods, high-performance methods for two network dimensions, and a naive approach for the other? And the second question is the visual analysis enhanced when using the combination of three methods, high-performance methods for the three network dimensions? To answer the two raised questions, in our evaluation, we analyze combinations involve the three strategies that we discussed. For example, here we have node ordering. The algorithm that we use for testing node ordering are time of birth, appearance, ascending node degree, and community-based node order. The second strategy is edge sampling. In the first case, no sample is performed. In the second case, bundle sampling. And the third, SEVs. Finally, for Timeslice, in the first option, we kept the original temporal resolution of the network and also applied the adaptive resolution. For the case study present in the paper, we use SAC dynamics, which means that all nodes start as susceptible except the infected patient 0. Each interaction involving an infected node and one of its susceptible neighbors has a probability p of infecting such neighbor. Nodes do not recover. So in this model, a node is susceptible, and with a probability p, it can be turned into infected. For the evaluation, the default executor order is: first we apply Timeslice, then node ordering, then edge sampling. For numeric evaluation, we use the number of edge intersections to quantify the visual clutter, and also the Kolmogorov-Smirnov measure to compare the network structure before and after the sampling. For visual evaluation, we first perform pattern identification using MSV, so we can check if the reduce of the visual clutter helps in the pattern identification. And we also perform simulation of infection spread using SAI and analysis of the transmission path. So we first simulate the infection in the network, then we perform Timeslicing, node ordering, and edge sampling, and we can check and evaluate the transmission path after these clutter reduction operations. Here you can see the first results of our combinations. We will perform the task of pattern identification using MSV. In these 4 examples, we can see a visualization of part of what we call museum network. This network is a contact network between the visitors of the Science Gallery in Dublin, Ireland. It has 72 nodes, about 7,000 edges, and 1,300 timestamps. In all cases, we use adaptive resolution with window size of 100. So in each visualization, we use different approaches for node ordering. Here, for example, appearance and CNO, and also for edge sampling. Here, no edge sampling, SCVs, no edge sampling, and SCVs. Let's now discuss these four results and compare these visualizations. In the first case, we use appearance node ordering and no edge sampling. In this case, the visualization is very dense and with several intersections. It is very hard to perform a visual analysis using this network. In the second case, we still use node appearance for node ordering, and now we apply SEVs for edge sampling. In this case, several edges are discarded, so the layout is less polluted. We can now identify few groups, for example this one. However, we still have long edges, so the improvement from the first example is not so relevant for this approach. In the third example, we use CNO for node order. This means that now we can see groups of nodes in the visualization. For example, this one and this one. Also, we can see low activity interval in this region of the visualization. This same interval in the original visualization is polluted, so we cannot identify from this first visualization that this region has low activity. In the last example, we use CNO for node order and SEVs for edge sampling. The layout is now cleaner, and this allows us to quick identification of important patterns in the network. So with this combination, we obtain a significant improvement in the visualization and in the pattern identification tasks in MSV. Here we can see the second example where we will perform the task of pattern identification with transmission path layout. Here's the visualization of the museum network in the original temporal resolution, node ordering using appearance, and no edge sampling. The simulation of the spread of the disease was performed using probability 0.1. So the first strategy to reduce the clutter was adaptive resolution. With the application of adaptive resolution in the transmission path layout, we could preserve the edge distribution and also reduce the number of timestamps. The second strategy was the application of CNO, community node ordering. So now we can see groups of nodes, here for example, and here. And these groups of nodes are very important to study in the case of intra-community infection spread, for example. And finally, in the third example, we also applied SEVs for edge sampling. In this last example, we preserved some communities, other communities were removed, and other communities were changed. So only relevant nodes are shown in this layout, and we also perceive the changes in the groups. Conclusion and future works. In our paper, we demonstrated the superiority of combinations involving two or more high-performance methods compared with the adoption of a single method. Two methods help depend on the network characteristic and the combination parameter values used. Three high-performance methods help in all studied cases. In this presentation, I just show one case. In the paper, we have another network which uses the three high-performance methods. Edge sampling should be used as a complementary strategy, always associated with a high-performance node ordering. The node ordering is very important in all situations. Now we intend to perform new experiments with other methods and parameter values, test other layouts, for example animated node link diagrams, and conduct a user evaluation. All the experiments were performed on DynetVis. You can download DynetVis. It's a free software for network visualization. Reference. These are the main references that we use in this paper. The first one describes CNO. The second one describes SEVs, the sampling method. And the third one describes adaptive resolution. Thank you for watching this presentation. I'd like to thank CAPS and FAPES for financial support. And if you have any questions, you can contact me This is my email address. Thank you very much.